Okay, this is for John, and we have a 10 megahertz BK1476A. It's in remarkable shape, looks almost new. There's no physical scratches on it. A couple of calibration holes here; those are intentional. A place for a snap-on package for the test probes. Unfortunately, we don't have that, but it does have that leather side to it. And the front panel is brand new looking. There's no scratches anywhere. Very clean. The knobs are all in good shape. I did replace this one knob here, you can see. But I've taken it through some tests. I already know that it's working fine, but I wanted you to be able to see it. Right now, we're going to start we're going to test the vertical deflection. Right now, we are testing with one millivolt per division. So a 1 millivolt signal coming in will make that rise one division at a time on this gradical. I believe. Go ahead and try it here. Let's see. There's one. See if I can hold this so you can see the division there. I'll step it back. 1, 2, 3, 4. That's exactly what it's supposed to do. Jumps up one division at a time for each millivolt signal that came in. Let's go ahead and move to the 2 millivolt per division. Now at this point, again I'll try and hold this steady. At this point it's going to take 2 steps to get a division. Hang on a moment. I'm on channel B, channel 2. Alright, let's try this once more. 1, 2, 3, 4. So we've got 2 divisions in 4 steps. 5, 6, 3 divisions. So that's exactly what you'd want. Okay. And we will go to 5 millivolts per division. And for every step of this, I should jump 2 divisions. So I'm going to step 10 millivolts a step here. Okay, then we just jump 2 divisions. And then we jump 2 more. We're at the top of the scale. That's exactly what we expected. Okay. 10 millivolts per division. Should jump 1, 2, 3, 4. Perfect. This should take 2 steps to accomplish each division. 1, 2, 3, 4. There we go. 2 divisions, 3 divisions, 4 divisions. Perfect. So this thing is in excellent calibration for voltage on channel B so far. Alright, we are right now on 50 millivolts per division, and I should be able to jump 2 divisions at a time. I am. It's because I'm jumping 100 millivolts a step. Alright, we're going 100 millivolts per division. We should go up 1 division at a time. 1, 2, 3, 4. Perfect. Okay, we're in 0.2, it's 200 millivolts per division, so now it's going to take 2 steps for every division there. So we just 2 and we got 1 division. 3, 4 is 2 divisions. 5, 6 is 3 divisions. 7, 8 is 4 divisions. Okay. 0.5 volts per division. I think we're going to be able to go 2 at a time. 1, 2 divisions, oops, sorry, 2 divisions at a time. Okay, and 1 volt per division, we should go 1 step at a time. There's 1 division, 2 divisions, 3 divisions, 4 divisions. 2 volts per division, we'll go back down to 0. It's going to take 2 steps per division, so 1, 2, there's a division. 3, there's 4, the second division. 5, 6, third division. 7, 8. The last would be 5 volts per division. I'll be able to get a division for you here. We're going to do it. It'll take me 5 steps to get a complete division. So 1, 2, 3, 4, 5. Right on the division line. 6, 7, 8, 9, 10. There's 2 divisions. It's the limit of my calibrator here. So we've just tested the entire range of channel 2. We're going to move ourselves to channel 1. And we're going to test the same thing on channel 1. I'll try and do it a little bit quicker. Alright, let's see. We're going to start with the lowest range. And ourselves set up here. Here we go. Alright. Channel 2, channel 1. There we go. DC. Make sure we're zeroed properly. Okay, there's 0. And we're going to go 1 step at a time. 1, 2, 3, 4. Okay, perfect. Alright, we're going to go 2 millivolts per division. It's going to take us 2 steps. 2, there's 1 division. 2 divisions. 3 divisions. 4 divisions. Perfect. 5 millivolts per division. We're going to go 2 at a time here. 1, there's 2 divisions. 2 steps is 4 divisions. So that went well. 10 millivolts per division. We should go 1 step at a time. 1, 2, 3, 4. 20 millivolts per division. 2 steps at per division now. There's the first step. Second step is a division. Third, fourth step is the second division. 5, 6 steps is the third division. 7, 8 steps is the fourth. Perfect. Okay, we're going to go 50 millivolts a division. I'm going to put in a 100 millivolt step, and we're going to go 2 divisions at a time. 1, 2. There's 2 divisions at a time. Okay, we're going to go 100 millivolts at a step. So now this will be 1 step. We're going to go 1 division at a time. 1, 2, 3, 4. Perfect. Okay. This is going to take 2 steps per division. 1, 2. There's our first division. 3, 4 is our second division. 5, 6, third division. 7, 8, fourth division. Okay, we're on the 0.5 volts per division. We're going to go we're going to go 2 steps at a time here. Okay, there we go. Perfect. 1 volt per division. We're going to go 1 step at a time. 1, 2, 3, 4. Okay. 2 volts per division. We're going to go 2 per step. So here's 1, 2. There's our first division. 3, 4. There's our second division. 5, 6, our third division. 7 and 8, our fourth division. Every one of these is predictable and it's landing just where it needs to land. So, okay, we're going to go, this is 5 volts per division. We're going to go 5 steps. There's 1, 2, 3, 4, 5. We've made the first division. 6, 7, 8, 9, 10. There's our second division. 10 volts in. We got 2 divisions up. Perfect. All right. That's the testing of our vertical input scales. All of them on channels 1 and 2 checked out perfect. We're now going to do a frequency check of the time base. Excuse me a moment. I'm going to set you down while I switch the leads to the scope. Okay. Alright, we're going to put ourselves at a reasonable input voltage. It doesn't matter. We're not testing voltage at this point. We're testing reaction to frequency. Okay. Turn on our generator. I'm feeding the input from this Hewlett-Packard 3320B. It's a frequency synthesizer. We're going to synthesize the time-based frequencies that we need. Yeah. Okay. All right. Let's start ourselves out. Alright. Alright, what I want you to observe here is that in 10 divisions right now at the 10 millisecond sweep rate, so it's taking 100 milliseconds for this to come across, and I'm feeding in a 10 hertz signal, and our time base is showing us that we are taking 10 full divisions for a 10 hertz signal, and this is as it should be. If I went to 20 milliseconds per division, I'm getting 2 peaks, which I should, and at 50 I should be able to observe 5, although it's hard to count. 1, 2, 3, 4, 5. Going to be a whole lot more observable as we go the other way. So 10 milliseconds per division. Here's 5 milliseconds per division. We're going to take ourselves up to 20. And then we should be able to adjust our synchronization point so that we can see across the axes properly. Alright, we're starting at the left of the axis. We're hitting in the middle, and we're on the right perfectly. And this is at 5 milliseconds per division. We're feeding in a 20 hertz signal, and it's taken 10 divisions for us to hit that. And this is exactly what we'd expect. Okay, at 2 milliseconds per division, if I raise to 50 hertz, we should again see 1 cycle in 10 divisions. Adjust our crossing points here. Okay, we're hitting the left start part of the axis, we're hitting dead in the middle, and we're hitting on the right. So we are getting, for 50 Hertz, we are getting in 10 divisions at 2 milliseconds per division. We're seeing one cycle displayed. Again, time base is accurate at this point. All right, 1 millisecond per division. I'm going to go to a 100 Hertz. Okay, and at 100 Hertz, adjust my crossing point again. The left is starting right at the starting point of the axis. We're crossing in the middle of the waveform, and then we are hitting the right-hand spot of the axis perfectly. So 1 millisecond per division, 100 Hertz signal. It's taking us 10 milliseconds to display one cycle of the waveform, so that's 100 Hertz, which is exactly what I'm putting in from the synthesizer, so we know that's correct. Now we go to 0.5 milliseconds per division. I have to raise myself to 20 Hertz. This is 200 Hertz. Okay, and a slight adjustment here. Starting exactly at the left-hand point, crossing in the middle of the waveform, exiting on the right-hand point. This is 0.5 milliseconds per division, 10 divisions, so we have 5 milliseconds total. This is a 200 Hertz signal, and that would be 5 milliseconds. Alright, now we're going 0.2 milliseconds per division. We're going to go up to 50 Hertz. We see ourselves starting, crossing in the middle, and exiting on the right. 10 divisions for one waveform. We're 0.2 milliseconds per division times 10 is 2 milliseconds total. We're at 500 Hertz. That's 2 milliseconds for a period of a 500 Hertz waveform. Perfect. Now we're going to go to 1000 Hertz. Alright, we're at 1000 Hertz right now. This is 0.1 milliseconds per division, 10 divisions, that'd be 1 millisecond total. We're hitting the start, middle, and end points of the waveform perfectly. So we are displaying one full cycle of a 1 kilohertz signal on the screen. It's dead accurate. 50 microseconds per division, I need to go to 2 megahertz. Adjust my crossing points. Okay, we enter exactly right, we cross right in the middle, and we exit exactly right. We're at 50 microseconds per division. That would be 500 microseconds total for the period. We're running a 2 megacycle signal, so that would be correct. We're at 20 microseconds per division now. We're going up to 5 megahertz. I'm sorry, 5 kilohertz. We have a 5 kilohertz signal. We enter properly, we hit the half wave point, we exit properly. We've got a full 1 cycle display of the incoming frequency. 20 microseconds per division, 10 divisions, that would be 200 microseconds, which would be 0.2 milliseconds, which is 0.2 milliseconds. 5,000 hertz. 0.2, yeah. Okay. We're at 10 microseconds per division. We're going to go now to 500. Let's see, 10 microseconds per division. 10 kilohertz. And 10 kilohertz, we have 1 kilohertz would be 1 millisecond per division. 10 kilohertz would be a tenth of that, so 0.1 milliseconds per division. We're I'm sorry, 0.1 second per cycle, 0.1 millisecond per cycle, and 10 cycles at 0.01 microseconds is 0.1 millisecond, which is the period of a 10 kilohertz signal. Wow. Mind is getting a little boggled right now, sorry. We're going to go to 20 kilohertz. We are at 5 microseconds per division, and we see the totally perfect waveform, one full cycle. So we're at 5 microseconds per division. That would be 10 times 5 is 50 microseconds across the screen. 50 microseconds is 0.05 milliseconds. 1 millisecond would be 1,000 hertz. 0.1 milliseconds would be 10,000. 0.01 would be 100,000. So we're halfway between 10,000 and 100,000. No, that's not right. 50 microseconds. That would be 20 kilohertz for 50 microseconds total. I could use a calculator at this point. And we go to 2 microseconds per division. We're going to go up to 50 kilohertz. Again, we see one full cycle displayed on the screen. We are running at this point 2 microseconds per division, so times 10 would be 20 microseconds. 20 microseconds is let's see. One microsecond would be a megahertz. 20 microseconds would be a fifth of that, so that's not right. Oh, excuse me. Let's try this again. 2 microseconds times 10 divisions is 20 microseconds. 20 microseconds, 1 over 20 microseconds, that would be 2 goes into 10 5 times. So this is 50 kilohertz. Sorry. Alright, once more. We are at 1 microsecond per division. We're going to go to a megahertz now. No, let's go to 100 kilohertz. Here we go. 100 kilohertz. We got one full cycle displayed. We are at 1 microsecond per division, but we got 10 divisions. So that's 10 microseconds. And with 100 kilohertz, that's 10 times faster than it's 100 times faster than 1 kilohertz. So 1/100th of of a millisecond. Would be 0.01 milliseconds, which 1 microsecond, 10, which would be 10 microseconds, yes. So we are 10 microseconds, that's 100 kilohertz. And if I go to 0.5 microseconds per division, I should require 200 kilohertz, and as we see, we get exactly one cycle in 200 kilohertz. So our time base is measuring accurately. We are able to see our synthesized signal, which is accurate to within 1/4 of a hertz, and in every range step. So beautiful time base, beautiful vertical. You got a good scope here. It looks great. It's functioning great. I think he's going to be very happy with it, John.